Hey, and welcome to the Deep Dive. If you're looking out at the Rockies today, maybe on your commute, especially if you call this amazing place home, you've probably wondered how these giants even got here.
It's a great question.
Yeah, and that's exactly what we're digging into. We're using a geology lecture by Nick Zentner as our guide here, and, well, the story of how the Rockies formed is maybe a bit more complex, even controversial than you might think.
Absolutely. For a long time, the standard story, the main idea, focused on pressure coming from the west. Think about the ground under California. There was this oceanic plate called the Farallon Plate.
Okay.
And it was diving, sort of sinking, beneath the edge of North America, subducting.
Right, subducting. So California felt this first, like directly.
Exactly. That downward push, that pressure, it built up California's coast range, the Great Valley in the middle, and it fueled the volcanoes that became the Sierra Nevada mountains. Sort of like the Andes in South America, that kind of volcanic chain.
Okay, so that was happening when exactly?
A long time ago. We're talking roughly between, say, 120 and 85 million years ago.
Got it. So California gets its mountains, but that still leaves the Rockies like hundreds of miles further inland. How do they connect that?
Yeah, see, that's where the traditional story had this specific twist. Around 85 million years ago, those volcanoes in the Sierra Nevada, they just stopped, went quiet.
Stopped? Why?
Well, the theory was that the angle of that sinking Farallon plate changed. Instead of diving down steeply, it started sliding underneath the continent at a much shallower angle. Picture like a flatter wedge going under.
A flatter wedge, almost like trying to slide a thin cookie sheet really far under a rug.
That's a great analogy, exactly.
Right.
And this shallow, flat slab moving eastward way underneath the continent started sort of tickling the underbelly of North America, much further inland.
Tickling? You mean lifting?
Lifting, exactly, pushing things up. And that uplift, far from the coast, is what supposedly created the Rocky Mountains. And it happened in a couple of main styles. You got these big blocks pushed straight up, like basement uplifts in Colorado, and Wyoming geologists call that the Laramide orogeny.
Okay.
And you also got more sideways pushing and stacking, like shoving layers of rock over each other.
Yeah.
That's the Sevier orogeny, which you see a lot up in Montana and Alberta.
Wow. So this one plate way out west doing the shallow slide thing was responsible for all this mountain building right here.
That was the prevailing idea for decades, yeah.
And now, are the Rockies still growing?
Generally, no. The main mountain building event, that Laramide and Sevier stuff, pretty much wrapped up around 50 million years ago. Though ranges like the Tetons, they're a separate, much younger story.
Okay. But you mentioned controversies earlier. This old model, it sounds neat, but maybe too neat.
Well, there were always some, lingering questions, like why did that plate suddenly decide to go flat? That's a big change. And why did the whole mountain building process just stop around 50 million years ago? The answers weren't totally clear.
Right. Which I guess brings us to the newer ideas, the challenges to that flat slab story.
Precisely. We have better tools now to look deep inside the Earth. We use earthquake waves, kind of like a CT scan for the planet.
Okay.
It's called mantle tomography.
Okay, like an X-ray deep down.
Sort of, yeah. And these scans, they haven't found that big, flat slab of the Farallon plate under the Rockies where the old model predicted it should be.
It's just not there.
Not in the way they expected, no. That's a pretty big blow to the flat slab theory.
Except the flat slab isn't there. What are these scans showing? Anything interesting?
Oh, absolutely. What's really fascinating is they have found this huge, incredible thick, folded up slab of what looks like old Pacific Ocean floor, but it's much, much deeper. And it's way over on the other side of the continent.
Wait, under the East Coast?
Yeah, beneath the east coast of North America. Imagine like a giant ribbon of rock, all crumpled and folded, sinking slowly down into the mantle.
Okay, that's wild. Pacific rock under the Atlantic side. How on earth does that explain the Rockies back here in the West? That seems total disconnected.
It does at first glance. But this leads to the newer interpretation. The idea is maybe it wasn't about a smoothly changing slab angle. Maybe it was more dramatic.
Like what?
Like a collision. The thinking now is that around 100 million years ago, North America was drifting westward, right? After the breakup of Pangaea. And as it moved west, it might have actually slammed into something big out in the ancestral Pacific Ocean, maybe a large microcontinent or a chain of volcanic islands, something relatively fixed in place.
Whoa, so less of a gentle slide under and more like a continental fender bender, a pileup.
Kind of. A massive pileup, yeah. And that collision, that intense compression, could be what squeezed and thickened the crust, pushing up the Rockies, both the blocky Laramide type and the folded Sevier type.
And the weird slab under the East Coast.
The collision could have also sort of pinched off or broken that sinking oceanic slab below. Then, as North America continued to move west over it, that broken piece just kept sinking downwards, eventually ending up deep beneath where the East Coast is today.
That is a completely different picture. A lost continent collision built the Rockies. Is there evidence for this smash-up idea?
Well, the timing fits pretty well with when the Rockies were actively being built. And geologists find these things called exotic terrains embedded in the western edge of North America.
Exotic terrains, like bits of land that don't belong?
Exactly. Chunks of crust with totally different geology than their surroundings, suggesting they came from somewhere else and got sort of plastered onto the side of the continent during collisions like this.
Huh.
They're still debating exactly where this collision boundary, this suture zone, is located. Some think it might be hidden in the foothills of the Sierra Nevada, interestingly enough.
So it's like North America was the bulldozer hitting a stationary island chain.
That's a decent way to think about it. A bit like how Australia, right now, is moving north and colliding with island arcs in the South Pacific. A moving continent hitting something more stationary.
Wow. Okay, so the mountains we see every day, the ones that feel so permanent, might be the result of this incredibly dynamic, almost violent event from the deep past, not just a simple plate sliding underneath.
Exactly right. It really shows that the story of our landscape is constantly being rewritten by new discoveries. The Earth is incredibly dynamic, continents drift, they collide, and these huge events shape everything we see.
It definitely makes you look at the landscape differently. Makes you wonder what other familiar features around here might have equally surprising or debated origin stories hidden beneath the surface.
It certainly does. There's always more to uncover.